And yeah, we're about halfway there on people. We'll continue to get a few more. But let's go ahead and dive in. As I said in my message, I've finally finished grading. Just took a little while to get my copies. Someone's got to unstaple them all and scan them all in and then email them to me. And then I have to parse them all out and that type of thing before I can even start grading. But they're done now on the exam. So I think I'm caught up on grading. If you've turned in a MATLAB assignment fairly late, then yeah, I haven't gone back and updated, gone back to grade any late ones. If you turning something in late, you're gonna pay a little price. As I think I mentioned in the beginning of the semester, that there are times in your professional life where due dates will be very soft, and it's easy to just get an extension or whatever. That's kind of how I ran my unmanned autonomous vehicles course last semester. But there's also times when due dates are very important, and I think I probably shared this, but a colleague of mine was trying to submit a grant proposal for phase 2, had done a great job on phase 1, but they needed to get a signature of support from a general or colonel or someone. I'm not exactly sure who it was. I think it was a general. And those guys are busy, and it didn't come through in time. And I think they were something like 7 seconds late submitting it online, pressing that submit button by the time they got everything done. And that proposal was never even looked at. Fantastic proposal, would have done great work for the Air Force, fulfilled a need. But yeah, rules are rules. So that's how we're running this course, right? So I will look at your assignments, but you're not going to get full credit. Now, a few of you all have had situations come up and have contacted me beforehand and said, yeah, I'm not going to be able to do it. And I'll deal with things on a case-by-case basis, but don't just ignore the due dates and, turn things in, whatever. That's not going to work for this course. So I hope that's clear. Just like I say, sometimes in professional life, we've got hard due dates and sometimes we don't. So let's go ahead and look at the exam then real quickly. Let's see if that's going to share. Bring it up. Doesn't seem to be rendering yet. Let's try that again. Maybe it's because I had it collapsed at first. Okay, I think we're going to get there. Good. All right, so hopefully everyone can see this, and we'll go through it real quickly. All right, so this question I put on the previous exam and last year, and everyone had a hard time with it. I rewrote it a little bit, and I think this time most people did pretty well with this, right? So entropy is the measuring the surprise or uncertainty in the data. That's kind of colloquially explained, but it's a measure of information, right? So I think we did pretty well with this. On here, this Shannon's capacity theorem, if we go up here, you can identify this as that equation. A lot of people did that. They note that this is the bandwidth. So if you increase the bandwidth, you directly increase the capacity. If you increase the signal power, you will increase the capacity, but kind of at a log base 2 level. If you decrease the noise power, then you can also increase capacity because that's in the denominator. Now, some people said, well, if you increase the signal noise ratio, so they group these two together, the S over the N, and that is known as the signal to noise ratio, right? Expressed in powers, but of course, as a ratio, the powers cancel out, the units cancel out. So then they struggle to try to find a third thing, right? So, sometimes maybe you try too hard on these things. And no, it was as simple as that, just identifying these three variables and, identifying this as that equation, and then identifying the variables and, knowing them, right? So, when you answer a question like this, don't just say B, right? I want to know that you understand that B represents the bandwidth that you're using, and S represents the signal power and that type of thing. All right, we had a hard time with this. Maybe I didn't kind of emphasize it enough. I think one of the things that kind of tripped you up, and I was kind of doing this. So when we look at this diagram, at one level, it's the individual blocks in a system, right? But I say kind of what models, right? So now we look at, all right, now sometimes we're implementing things, sometimes we're modeling or simulating things, right? So now we're simulating things, and it's really this channel that models the effects of transmitted signal. So a lot of y'all recognize that the channel is what we use to send the signal, right? It might be free space, and a lot of cases could be wires, could be fiber optics, could be waveguides, that type of thing, right? So, but here it's where we're going to model all of those impairments on the transmitted signal, right? So we're forming up the signal as we go along here, and now we're ready to transmit it. And in this channel, there's power amplifiers, there's frequency up conversion mixers and that type of thing. And then there's low noise amplifiers on the receiver side. But there's also noise in the environment. There could be Doppler shifts. There could be a lot of these things. So we haven't gone into all these details yet. But yeah, sometimes I'm asking questions that kind of require you to make a little bit of an advancement in your understanding of things, right? So here we're kind of changing the discussion from an implementation to a modeling type of thing. All right. So all right, we did pretty well on this one. What are the three features of a signal? Yes, there's you can actually kind of do things with time and that type of thing, but these are the main ones, right? And you actually did some of this in your MATLAB exercises, right? So you did an amplitude modulation, and we talked about frequency modulation and phase modulation, right? So these are the things that we manipulate in order to be able to convey that information. All right, then, what are three examples of randomness in communication systems here? I'm kind of looking for three distinct different ones, and to be a little bit precise about this, so maybe you didn't get full credit because there was a little bit of redundancy if you're saying that, like, there's thermal noise and noise, right? So, be specific on these things, right? And here I'm just giving you a few examples. These are mostly off the slides, but yes, there's thermal noise, also known as Johnson noise, and again, that's due to the kind of atomic or scale vibrations anytime you have noise, temperature above absolute zero, you have some motion, right? And that leads to Johnson noise, also known as thermal noise. And that shows up predominantly in the amplitude of things, right? Then we have the path length and the mobile communication system. We might change the relative positions of the receiver and the transmitter on a varying time varying basis, and that's going to manifest as a phase change in the signal. Call initiation rates, yeah, I kind of toss that out there without explaining a whole lot, but as you can imagine, a cell phone tower, and then people are picking up their phones and starting a call, right? So there's some randomness associated with that, and we have to. It's a little bit higher level than what we will really explore in this course, but it's just another thing that you have to consider as a communication engineer. How loaded down will that base station be, right? And the input data itself, right? So it could be voice. There's a randomness and what word I'm going to say next, right? Maybe generative AI or large language models are starting to be able to predict what word I'm going to say next and stuff. But so it's not completely random. There's some structure to it, but music, data can be random when we look at it in our system, right? So reflections of the waves as they travel to the receiver. From the transmitter, you might bounce off buildings or ground or other things, and then they take a different length of time or path length to get to the receiver, and there might be some amplitude, some loss in that reflection. And typically we have multiple waves reaching the receiver, and some have traveled longer distances than others. And actually that means that the phase of the different signals, even though they start off at the transmitter the same, because they might take a little bit different path to get to the receiver through these reflections, then their phase will be a little bit different, and they will constructively or destructively combine or add in the receiver. And so we call that multipath interference, and we'll look at that more in latter part of the class. So, all right. So then on number 6, we looked at some uniform random variables. Most of y'all found the appropriate equations out here that I added. Of course, you need to understand the notation and that type of thing, and stuff. But that's pretty simple as long as you recognized it. A few of y'all didn't recognize it and tried to kind of use this equation, and that's a lot of steps. That was not intended. It was intended that you kind of observe that these equations exist and be able to plug and chug. And it's just a little bit of arithmetic. If you made an arithmetic mistake, a tiny ding. I'm mostly looking for you to recognize these things and how to apply formulas, right? So if I'd ask for a Gaussian, it's actually even easier, because the mean there shows up in your equation, the mu, and the sigma there is the standard deviation, but sigma squared is the variance, right? So most did pretty well on that. This one was hard, and I tried to give you a lot of grace on the answer. If you kind of started getting in the neighborhood, meant to be easier than it was, right? So the idea here is, are you really understanding the idea of conditional probability and versus statistical independence? when we say that, what is the probability of A given that B has existed, has occurred, right? What is that probability? Well, if events A and B are statistically independent, then this equation basically simplifies to this, because there is no conditional effect that's going on there, right? So you can kind of derive this by expanding this union here, this probability of this intersection, and then you would end up with being able to divide out the probability of B's here. Few of y'all try to use Bayes' formula. You don't need to do that here. Yeah, that's good, because you're kind of seeing how that's how you might flip the conditional relationship around to try to find the probability of B given A from the probability of A given B. But here we're statistically independent, so there is no real conditional probability, right? So it just simplifies to this. Okay, so then, yeah, so you can look at this. I know that, I said we're not going real deep into wide sense stationarity and ergodicity, but still want you to understand the kind of high level concepts. And I gave you a choice to try to pick the one you understood better, maybe, and stuff. So we did okay on this one. But basically, real simplistically, wide sense stationarity, or stationarity in general, means that we don't need to worry about the time origin, right? When does time zero actually start, or absolute time, right? We're really looking at the differences in time. And autocorrelation is kind of that, or cross correlation is looking at how signals compare at different time intervals, deltas, right? And but we don't have to worry about when it all started, right? So we can just look at the time differences, and that enables things like being able to calculate the power spectral density through a Fourier transform of the autocorrelation and that type of thing. I think there were a couple of people that picked up on that. Ergodicity is the idea that in a random process where we might have time varying signals that, but we don't know which one we're going to get because it's a random process, right? So we might get a time varying signal that squiggles in one way versus squiggles in another way, right? And that random process, to be able to calculate statistics without ergodicity, we would need to be able to run an experiment where we would draw a number of different signals from that random process from a sample space, and then hopefully gather up enough that we can calculate some statistics and be able to calculate the mean and standard deviation and that type of thing. But ergodicity allows us to kind of use the time-based statistics as a proxy for the sample-based statistics. So we can choose to only analyze one time varying signal, but be able to look at those statistics over time. Granted, both of these explanations that I'm giving you, there's a lot of hand waving going on here. So if you do go on to graduate school, you're going to learn these things more rigorously. But these, the way I'm explaining this is kind of the high level concept that I hope you can get and master, right? So, all right. So here, this one we had a little bit of trouble with also. It's actually, I showed all the math with the trig identity, with the cosine kind of double angle formulas and that type of thing with omega 1 and omega 2, and you kind of combine them together using some trig identities, right? But the takeaway is very, very simple. So let's drive that point home, right? So when we're mixing in RF systems or communication systems, whatever, we're doing this nonlinear mixing, then we're going to end up with a number of different frequencies. We're still going to get the original signals out, right? So they're going to come out also, right? So if you think about how I did that little power series or Taylor series approximation and stuff, I kind of started with Taylor series and then simplified it to just a power series. You still have kind of that linear term, right? So you'll still have the 10 megahertz and the 5 megahertz signals coming out. Now, most of the time, the ones we're interested in are the difference and the sum, right? So we get those, right? So 500 minus 10, 500 plus 10. Yes, technically there's a 10 minus 500 and such. So I'm only including the positive frequencies here. But there's also, if you go through that math, you'll see that, well, there's a sum of this signal also, right? 10 plus 10, right? So we had 500 plus 10 gives us the 510, but just 10 plus 10 gives us 20 megahertz. And 500 plus 500 gives us 1,000 megahertz. Now, during the exam, I realized maybe if someone's really mastered this and very mathematically based, they might recognize, well, their nonlinear device could have third order nonlinearities or fourth or quartic or and so on. So that's why I kind of limited it to second order or power of 2. There's also a situation where now if you have a fairly nonlinear device, then like this signal would mix with this signal, right? And so because that's existing in the output of the circuit where the nonlinearity may be, right? So then you can have kind of multiple orders, right? But so strictly speaking, maybe this isn't all the frequencies at the output, but these are the dominant ones. Now, most of the time we're going to if we're interested in this one, we're going to filter all the others out, right? Or we're going to design our nonlinear mixing circuit such that these signals cancel each other, right? So they appear kind of equal amplitude but opposite phases. If and so maybe the 10 megahertz will cancel, the 500 megahertz will cancel. We can easily filter these out, and then we can kind of figure out how to select one or the other. That's really a circuits course. There's definitely techniques to do that so that in the end we could just have one of these, right? But fundamentally, you're going to have all of these, right? So yeah, all the math I did with the trig identities and that type of thing, it's a little bit complex. Just know that when we're doing mixing in an RF system, then you're going to have sum and differences and the original signals also. So maybe it's easier than it looks at first glance. All right, so then why do broadcast transmitters send a carrier along with sidebands and amplitude modulation, right? So I try to make this a little bit easy on you by giving you these two questions right next to each other, right? Because if we look at question 11 here, this is showing the more complex version of the receiver where we're having to generate a carrier to demodulate this, right? And we end up with this, difference signal here or this, nonlinear product signal here, right? So, and then we have this 1/2 MT. And actually, when we do this one, we end up with kind of those trig identities again. But if we make W1, omega 1 equal to omega C here, and we make the thetas equal? Well, there is no theta up here, so theta is 0, right? Theta sub c would be 0, so we make this theta equal to 0 also, right? If this theta is 72 degrees, then this theta needs to be 72 degrees, right? So the point is we got to match these. What that does is that then gives us here, we get this multiplication of mt cosine squared omega ct. And then we do that little trig identity, and we end up with a 1/2 plus cosine 2 omega ct, something like that. And the low pass filter filters out that cosine 2 omega ct, right? And that's how we isolate this 1/2 mt, right? So the problem here is that this is a coherent AM receiver, and yeah, we didn't really go into what we mean by coherent, but what we do mean is that these things match, right? And all the way down to the phase, not just the frequency, but the phase also. So you need some fairly sophisticated circuitry to kind of sniff this signal and to regenerate this that tracks this signal, right? Because as things move, you have some mobility. Well, there's actually going to be some phase shifting going on here, and possibly some Doppler shift on this omega. So we have to track all of that, right? So these are the conditions that have to be satisfied for that. And, that would be a circuits course. So it's a little bit different course, but how to implement all this. There are techniques, tracking loops to do this, right? Your book talks about them a little bit, but it's really beyond the scope of this course. But that's what makes this hard, right? So in the broadcast situation, not every amplitude modulation or frequency modulation station is a broadcast system, right? A lot of times they're two-way, point to point, and there's two radios trying to talk to each other, right? So, but here in broadcast, we have one transmitter, many receivers, right? So the idea is we want to make the receiver cheap and easy, so we don't have all these tracking loops in there. So the broadcast transmitter sends along a little bit of carrier along with that. So that allows us to simply use this envelope detector that's that diode and an RC circuit with a time constant such that it can kind of trace out the kind of peaks of the envelope on that modulated signal. And the RC circuit does a little bit of low pass filtering, and we end up with that, right? So we end up with the signal. So all right, so I'll explain both of those. Major advantage of frequency modulation over amplitude modulation. Yeah, we had a tough time with this one also, and I think it's because we got a little bit behind, and we didn't go into FM as much as what we might have. I've also said that we're not going to really explore analog modulation that much. But a lot of you tried to relate the comments that I had made about the sidebands of FM and how they actually go off to infinity. And if you would study analog frequency modulation, then you like the next step would be to go into great detail on how to calculate those sidebands and how far out they go. But they're spaced a little bit according to the frequencies of the modulating signal, but also since FM is taking the amplitude of the modulating signal and translating that into a frequency deviation, then that means that the relationships get a lot more complex. So, but actually, the more that FM, because it's side lobes frequency content technically goes off to infinity, is actually problematic, right? It's not really an advantage. It's can be a disadvantage. It takes up more spectrum. Now, fortunately, they roll off, but AM sidebands are finite, right? So they're going to occupy only a certain amount of bandwidth based upon the frequency of the modulating signal, and that's it. Boom. So instead, what I'm looking for here is that frequency modulation has a constant envelope, right? So when you look at the modulated carrier, you'll see that the sine waves sometimes are squeezed together, sometimes pulled apart, right? And if we look at it in terms of the period, but that's that frequency variation, right? If we're looking at a wave, a frequency modulated wave in a time domain, but it's always the same amplitude overall, right? The peak to peak amplitude is always the same. It's what we call the envelope, right? And that means that we can actually use more efficient power amplifiers, and it's which again delves into the circuitry, microwave circuitry design of power amplifiers. It's a fairly advanced topic, one I worked on for several years in my career and really enjoyed. But again, beyond the scope of this course, but I put it out there that it is easier to efficiently amplify a constant envelope type signal. So the other thing, which is perhaps more obvious, is that many of our noise sources are in the manifest in the amplitude domain, right? So if we have some thermal noise or some static from lightning or high voltage transmission lines, power lines, whatever, that amplitude variation, that noise gets impressed right onto the AM signal, and comes right out to the modulated signal, and we end up with a very noisy result in AM modulation. But in FM, it doesn't matter because we're not interested in the amplitude excursions, right? So if we add a little power or a little bit of signal in the amplitude domain for for an FM signal, we're only really looking at the frequency deviations, right? So it's the kind of essence of frequency modulation. All right, and then finally, where we looked at this was a little bit kind of last minute addition. We just covered this lecture last Tuesday, but the idea here is that we're mapping multiple bits to a single symbol out of a set, right? And then I kind of give you a hint here that k is equal to 3. That's what that means, right? So we're mapping 3 bits to a set of symbols. And yeah, I'd originally had it as 5, and I decided to make it easier, but I forgot to change that in the text here, right? So how many different symbols in a symbol set are required to transmit any combination of those 3 bits, right? Trying to give you as much information as possible. And so most of y'all recognize, all right, so you pick up on that K and you go down here and you find this equation. And some of y'all struggled on what to do with that, right? So you're trying to solve for M. Well, not sure what grade you learn logarithms, but by now you should recognize that the reciprocal operation of a logarithm is exponentiation, right? So I know, not trying to harp on you or anything. It's in the stress of an exam, sometimes some of those things don't pop out at you, right? But that should be something that is well learned by this point. So if that's not obvious to you, then go back and brush up on logarithms and exponents a little bit. But if we've got something that's where, let's see, k is equal to log base 2 of m, then we can say that m is equal to 2 to the power of k. Come on, right there, right? And so now that pops right out. 2 to the power of 3 is 8. So that should be your answer, 8 symbols, right? Now, we only transmit one at a time, right? So down here, we've got, I put this comment in most of y'all's that didn't get this, but this is really 1 million or mega bits per second, right? And then we're dividing by 3 um, uh, bits per symbol, right? And so I don't know where I learned this trick with units and canceling them out. I think it was maybe chemistry when we're dealing with moles or something like that, right? But even if you don't really understand this, if you're faced with something like this and you've got these units, then put it in a way that you can cancel units, right? So here we're dividing because we don't want bits in our answer. We want symbols per second in our answer, right? And so we know we've got some bits per second, so we need to divide by some bits to cancel that unit out, right? So what do we have? Well, we've got this k is equal to 3, so that's 3 bits get mapped into a symbol, right? So then we divide by this 3 bits per symbol. This is in the denominator, but it's also in the denominator of this thing, so it comes take the reciprocal of that, and it shows up in the numerator now, and so we end up with symbols per second, right? So the second is in the denominator there also, right? So that that's how that one's done. A few of y'all got that mixed up. A few of y'all didn't even kind of recognize it, right? So some people tried to multiply it or whatever. So just as a hint, and maybe it's a little bit of test taking, tricks, but look at what information you have and try to cancel out the units algebraically such that you get the answer that you want. Now, you do need to realize that this is this k is equal to 3 is mapping 3 bits to a symbol, right, in this set, right? So, all right. So, yeah, let's move on then. One last thing. So, yeah, our mean, maybe if you ignore grade inflation, that's maybe where we should be, the mean or the median. Yeah, I know probably most of y'all expected this averages to be a little bit higher. maybe instead of in the C range and the B range, but it is what it is. We're fairly grouped together. There were some that did quite well and some that did not quite so well. But that'll kind of help you be able to kind of place yourself within the grand scheme of things. But yeah, so we'll this exam was really more of a quiz, as we said. So it's going to account for 10 points towards your final grade. So not trivial, but not life-ending, right? So we'll be able to move on from there. Not sure, if I'll, some people asked if there's any way to make up, or if there'll be a curve or anything like that. We'll figure out any of that type of information towards the end of the course. But yeah, again, I just want to make sure everyone does well, and we'll get there. So, all right, so let's now try to get into our presentations and. All right, so come on. There we go. Actually, there is an assignment. I think it's due Thursday night. Tried to, when I originally structured the course, I tried to not make assignments due when our tests were happening and that type of thing. But we're a little bit off schedule. We will make things up, and also, but yeah. So that assignment's due on Thursday night. A couple of y'all have already turned that in. I did kind of walk you through that assignment last Tuesday on that lecture. So look that up if you're having problems on it, or make an appointment for office hours tomorrow or Thursday. Then I have not prepared a new assignment yet. So we'll just kind of take a deep breath. We'll cover a little bit more material here as we move ahead, and then I'll start doing some more assignments quickly. So let's go back and review a little bit. So we went through and we came up with this idea of representing our signals as vectors, right? Where now we can have some sort of orthogonal basis function, and then once we've done that, and we didn't, and we won't go into great amount of detail on how do we derive these basis functions, except noting that it's kind of similar, to the way Fourier expansion works, Fourier series expansion, and that type of thing. And a lot of times that's exactly what we'll use for our basis function, some sort of cosine or exponential, complex exponential, something like that. But there's other basis function we can use. Ultimately, this coefficient, the idea that now we can represent our signal as some set of coefficients here, allows us to basically formulate something where ultimately we've got these constellation points. Here they're shown in complex space. So this vector here, this signal, could be represented by a coefficient along this real axis and one along the imaginary axis, right? And you see we've kind of spacings out here nice and uniformly. That's done for reasons. It doesn't have to be, right? So there's not anything intrinsic in this state space representation or vectorization of these signals. It says that these are all kind of symmetrically align, but as we go through our discussions of these waveforms that we use for digital communications, you'll see that there's reasons for this, right? So, and we talked about memoryless, is that if we take some K set of bits here, and then they're going to be mapped through this modulator to one set of symbols out of this symbol set, right? So, and each group of K bits, as this information stream is coming in, produce a symbol, and they're independent of any of the other groups, right? So there's no memory. It's just a direct mapping, 1 to 1, 2 to 1, 3 to 1, 4 to 1, 5 to 1, whatever K ends up being, right? Then we looked at, kind of talked about this concept that, well, we could have some memory involved also. And we're just kind of introducing this as a concept, and we'll come back to revisit it, but just understand that some modulation systems are memoryless and some have memory associated with them. All right. So, and the number of past bits that were kind of reviewing or incorporating in our output, we kind of refer to that as L, right? So one current bit and L minus one past bits. So L is then called the constraint length, and we will often implement this with a finite state machine, and we need to have this 2 to the L minus 1 times K states, different states to deal with. And so we have this kind of output mapping function, and we also have a state transition mapping function, right? So, all right, then we looked at a little bit of this idea of the sending a symbol every t seconds. This was your question 13B on the exam. And so then we looked at some energy. And I think by this time we were moving pretty quickly, but the idea that, well, if we have these bits coming in and some number of bits produce some number of bits produce a symbol, then if we look at the average symbol energy, then we can allocate that symbol energy to some individual bits, right? So if there's 3 bits that go into making a symbol, and that symbol has a certain energy, then if we want to allocate the energy down to the bit level, then we divide it by K, right? Which is also equal to log base 2 of M, right? Where M is the number of symbols in your symbol set, but K is the number of bits that goes to make up a symbol, right? So we take K bits, we choose, we have an algorithm mapping that chooses a symbol out of that symbol set. We transmit that. That takes a certain amount of energy. We're just allocating that energy to the individual bits, right? On average. And this is just saying, well, let's just take all of the symbols out of our symbol set and average them. This is the probability that we'll have a particular symbol. Most of the time, we're dealing with equal probability symbols. So this would just be, 1 over M probability, right? So of any single symbol. If they're all equal probable, then T sub M is just 1 over M. All right. And then we looked at pulse amplitude modulation, right? So now we're going to create a symbol alphabet using different amplitudes for the signal. So we're going to have some pulse that we're going to send, right? And that's generally going to be defined from 0 to capital T, for one interval, and then we'll send another symbol and another symbol, right? So at first, our symbol would start at t is equal to 0, and then the next symbol would be sent at t is equal to t is equal to 2t, t is equal to 3t, but each time that symbol is finite over this duration t. Now, a simple pulse would just be a square pulse, right? But sometimes we use something a little bit more sophisticated, right? So that pulse might be just a square, but it might be kind of rounded also, and we'll talk about the reasons why. So its shape is an important design factor, and we'll carry that. We'll look at that in later lectures. And so here we're looking at this AM here. This is going to be the coefficients of this pulse amplitude modulation. And yeah, there's a little, algebraic formula here. M goes from 1 to M, capital M, different symbols in our symbol set, right? And if you look at this, if you punch some numbers in, you'll see that it's balanced about the origin, right? In a one-dimensional system, right, along the real axis in this case, right? So this equation produces equal spacing about 0. So, and then we can plug that in, that relationship in for A sub m, and we'll just expand it out for various small m's, m1, m2, and so on, right? So that's just plugging m is equal to 1 into here. So we'd have 2 minus 1 is 1 minus m, whatever m is, and stuff. So that gives you this kind of relationship, and also which with some magic of series, finite series, you can simplify to this relationship, this m squared plus 1, and m times m squared plus 1 divided by 6. I mean, and then we can do some cancellations and get with this more simple thing. So like this, this part of the equation comes from this finite series here. Right? So, and yeah, there's, that's more advanced topic, but you can kind of trust me on that. So, all right. So, and then we can kind of relate this to the energy, average energy in the bits. Again, this is for this pulse amplitude modulation, right? And so now we're just dividing by log base 2 of m, or k, right, to allocate the average energy in the symbols to individual bits on average. All right, so then we look at a time domain waveform. I think I better kind of skip some of the review here a little bit, because we have already seen this, but I know you had a test in between, so you probably forgot it all. That's all right. So here's one way of drawing this this pulse amplitude modulation out. And again, we're ignoring what that pulse looks like. We're just looking at what those amplitude coefficients are on that pulse, right? So if m is equal to 2, then we can map it this way. Note that m is equal to 2. If we take the log base 2 of that, that's equals k is equal to 1. So there's 1 bit per symbol here, right? So, and I've just mapped it this way, somewhat arbitrary, where a 1 is going to be at this voltage level and 0 is going to be at this minus voltage level, right? So if we look at this, the average of these two, assuming that it's equal probable to send a 0 as it is a 1, then the average is going to be 0 here. That's kind of nice. We don't have some biased average on that waveform. If m is equal to 4, now log base 2 of that is going to be 2. And so we'll have mapped 2 bits into a symbol. So we need these 4 different symbols. Here I've kept this spacing the same. And we see that it takes more and more voltage ultimately to send all of these greater number of symbols here. Here I've done an m is equal to 8, so that would be k is equal to 3. Log base 2 of 8 is 3, or 2 to the third is 8. So 3 bits goes into mapping each one of these, right? So now we need lots more voltage to send this waveform. Now I added this diagram. There we go. Yeah. So here I've kind of redrawn that same constellation, but now changing the spacing, but keeping the kind of peak amplitudes the same between m is equal to 2, 4, or 8. And what we see here is that distance between these constellation points squeezes down more and more. So in reality, these things, by the time they reach the receiver, maybe some noise has pushed this thing around. Maybe it comes out over here, or maybe it comes out over here, right? And I think you can intuitively see that. Well, if at the receiver we see something that's kind of less than 0, we'll assume that this is what was sent. And if it's greater than 0, we'll assume that that symbol was sent. But note that, yeah, this if we sent this, then we could have so much noise that it might show up right there. And at the receiver, we might only be able to assume that that's a 1 instead of a 0, right? So that would be an error. And we're going to look at that. That's a big part of what we do as digital engineers, digital communication engineers, is try to look at what might cause that. Now, and be able to predict the rates of this based upon our signal noise of our system at the receiver. Now, that looks very unlikely that we would have so much noise that would move the signal from here all the way over here, right? But here, maybe we've got to expand our decision making a little bit more, right? So if it's less than 0, but let's draw kind of a line here, right? And then we'll draw one right here. I'm kind of skipping ahead. We cover these, what we call decision areas, later on in the course. But now we've got this region here, but then we've got this region here. And I guess I can change some colors. We might have this region here, and then ultimately this one over here, right? So now we can see that if when we receive something, it shows up right here. We're going to assume that it maps to this symbol here, right? But if it shows up right here, we're going to assume that comes, goes with this symbol, the same as with this one, right? It's going to go with that one. But now we see that if we sent this and we had some noise, then maybe the receiver sees it right there and is going to categorize it as this symbol instead of that symbol, right? And boy, that's a lot less distance that noise has to move that symbol compared to this one, right? Before we have an error, right? Here it's even worse, right? Here maybe our decision boundary is there, and now we only have to move that far before we have an error, right? So what you should be thinking is that, okay, so this allows us to send 3 bits of information for every symbol. That sounds good, right? But it doesn't come for free, right? We need to have lower noise or higher signal powers, right? Signal power would be how broad this is, right? But lower noise would control how much this deviates there, right? And so the number of symbols per second that we send is setting the bandwidth of our waveform. And so if we have to send 1 symbol for every bit and we want to send a lot of bits, well, it's going to take a lot of bandwidth. If we only have to send 1 symbol per 3 bits, right? And we still want to send lots of bits. Well, now we're only having to send 1/3 of the number of symbols on the channel, which means our bandwidth is going to be smaller. So we call this kind of concept a bandwidth efficient modulation, right? But it comes at the expense that we've got to improve that signal noise ratio, right? So now go back and think about Shannon's capacity theorem, right? Is this capacity is equal to the bandwidth times the log base 2. I'm going to run out of room here, but it's 1 plus the signal over the noise, right? So now we're seeing how all these different variables are coming into play in as this example of this constellation. Okay, so all right, so are all these equal energy symbols? All right, so I've shown you a couple of different versions of those. All right, so now let's talk about gray coding here a little bit. I think we either didn't get this far or we kind of hand waved over it, I think, in the last lecture. So this is starting to become new material here with 15 minutes left in the course, in the class. All right, so gray coding orders the symbols such that only 1 bit changes between adjacent symbols, right? So a noise spike might make the receiver think that the received signal is an adjacent symbol, right? So we kind of covered that here, right? So we said, yeah, we have some noise, and so if the noise is big enough, it puts us into across this boundary, and now we're going to make the incorrect assumption, right? So this symbol is sent, but the noise made it appear at the receiver over here. The receiver doesn't know any better. It just sees it here, and so it maps it to the closest symbol, which is this one, right? So that's an error, right? Now, let's look down here with the m is equal to 8. Here we have these symbols. If we make an error in this symbol, then we're not just making an error in a symbol, we're making an error in the bits, right? And there's 3 bits mapped to each one of these symbols. So that could be disastrous, right? We're not just making an error in a symbol, but we're making an error in 3 bits, right? Well, if we're careful about this. Let's make sure. Let's look at how these things are ordered, right? So if we look at these bits, so you see that they're not in numerical order as we start from here and go to there. They're in what we call this gray coded order. And if you look at it, only one bit changes between neighbors, right? So if we send this symbol, right, the ones that we're most likely to make a mistake about is either this symbol or this symbol, right? So if we send this one and we got some noise, maybe it comes out over here, or maybe it comes out over here, and so we're gonna still map it to that closest symbol, and we're going to make a mistake. But it turns out that since only one digit changes between each of these neighboring pairs, we're only going to make one bit error. Instead of making maybe 2 or 3, we're only going to make 1. So here we might assume it's 0, 1, 1 instead of 0, 1, 0. So we've got an error in this position. That one should be a 0. Over here, we would conclude if the noise pushed the reception of the symbol over here, then we would conclude it's this symbol and map to 1, 1, 0, right? Well, there we made an error in that position. But you'll notice that each one of these neighboring pairs only changes by 1 bit. If we had done this in order, it would have been 0, 0, 0, 0, 0, 1, 0, 1, 0, right? This value would be over here, right? If we did it in numerical order, binary counting, right? So this one would be over here. Well, in that case, we would make an error in both of these, right? So between this bit pattern and this bit pattern, right? So not only this would be a 0 instead of a 1, this is a 1 instead of a 0, so that would be 2 bits. So that's the idea of gray coding, right? So it makes an easy test question. Maybe we'll do a little exercise on that to kind of help reinforce that. But it's the idea that only 1 bit changes between adjacent symbols. So if we're going to make an error, we want to make it as least consequential of an error as possible. Okay, so I'd much rather make 1 bit error than 2 bits or 3 bits of an error. So, all right. So as we'll see later in the course, we can often correct a single bit by using these channel coding techniques, right? And that's where we add some redundancy in a structured way so that we can kind of compare things and detect and sometimes even correct a certain number of errors at the bit level. All right, so again, we will quantify the noise performance later, but let's define a minimum distance metric, right? So this distance is the key word here, right? So here we're looking at the distance between symbols in terms of voltage, let's say, right? And if we're using kind of a constant basis set, then these, we can look at these as just these vectors, SM versus SN, just a different symbol out of that symbol set, right? And they all have this average energy EP, and then we that's the energy, so we want amplitude here, so we take the square root of that. And these are the coefficients, right, out that are scaled by this energy value, right? So you can do the math here and expand it out, but here, if we then look at PAM, pulse amplitude modulation, this is going to be a generic process we go through, concept, but this is now specific for dmin. If we look at these guys, we got to go way back to this equation right here, right? Now, each of these varies by 1, right, as we plug in different things, right? Now, it might be scaled by this energy and this PT, right? But once we factor that out, then yeah, these are scaled actually by a value of 2. Sorry. So so this absolute value of AM minus AN, that's actually 2, not 1, as I misspoke there. But so that's our minimum distance, right? And then we can relate this down to the energy, average energy per bit, right? So this minimum distance, in this case, it's we use this kind of constant spacing. So this distance here is the same between these two symbols as is between these two symbols as between these two symbols, right? Now, the distance between here and there is more, right? It's 3 times as much, right? But the minimum distance in our constellation is what's going to set our noise performance, right? So if the D is larger, then we've got more noise immunity. It takes more noise to make a mistake. If D min is smaller, right, then it takes less noise to make a mistake, right? So that's our big metric there. And all right, so all right, so now we're kind of coming to the end of this class here. So we'll next Friday we'll look at phase modulation, and just real quickly, at m is equal to 2, it kind of looks the same. Well, it definitely looks the same as pulse amplitude modulation. Instead of this being plus A and minus A, perhaps, then it's actually A at an angle of 0 and A at an angle of pi radians, or 180 degrees, right? So that is essentially the same as going through 180 degrees of phase, right? But it also gives us this opportunity to generalize it now on the complex plane, right? Pulse amplitude modulation was just multiplying by that coefficient out front, so we were all on the real line. But now we're changing the phase. So here's pi over 2 radians, minus pi over 2 radians, or 3 pi over 2 radians. Here we split it up even more. So we're doing that same concept, but now we're just distributing these things differently. Note that in this case, all of these guys have the same energy, right? They're the same distance away from the origin, right? So if we kind of look at this in terms of amplitude, that's constant radius. So these are all the same amount of energy compared to the pulse amplitude modulation, where some of those are small voltages, some of those were larger voltages, right? So, but now we've got to distinguish in phase in this complex domain. All right, so we'll dive into that more on the next session, right? So if you haven't guessed by now, a lot of these next few lectures, we're going to be adding some information kind of gradually, and then kind of going back and filling in the holes and kind of reinforcing it. So it's going to look a little bit repetitive, but we are going to add information each time. So and kind of spiral in terms of detail as we do that. All right. So again, don't forget the assignment, the MATLAB assignment on random processes, random variables. That's due Thursday night. Okay, that's it. Thank you.
Thank you, Professor. Have a good day.